All right, let's finish this. So the fastest marathon, last I checked, was ran in Berlin in 2014 by Ms. Komodo from Kenya. His time was 123 minutes, round all parts to 3 decimal places. Now, this is not his actual time. Someone who took this problem rounded it up. So if you go check it out, his time is actually a little bit different. But this makes the problem simpler. We're supposed to calculate the unit rate in miles per minute. Well, for this case, that's quite straightforward, I think, because the number of miles is 26.2, and then we're dividing that by 123 minutes. That seems like a made-up number, doesn't it? And this gets us miles per minute. It is not a unit rate, it is a rate. So all we have to do is do this division to figure out what that unit rate is. So trusty decimals will help us out there. 26.2 divided by 123 gets us 0.21, 3 decimal places. Okay, 213 miles per 1 minute. Now, I don't quite understand that number very well. So let's do the minute per mile. This is a pretty common measurement for runners. I think you call it your splits. How fast is it? Can you run a mile in 1 minute? Now, keep in mind that this gentleman was doing this for 26.2 miles on average. So all we have to do is flip the rate we had before into minutes per mile into the division. Or we could have used the same one, 123 divided by 26.2, doesn't matter either way. They're both the same thing. So 1 divided by 0.0213, oops, by 0.213 is this value. Now, if we use the more exact values, because remember that one was rounded, so the 123 divided by 26.2, notice there's not really a difference out to the third decimal place either way. So this is approximately equal to 4.695 minutes per 1 mile. Does that not blow your minds? This guy's cruising. I don't even know if I could run a 4.695 minute mile just in one time. So what does this mean? Dennis, if I can call him that, I feel like I need to call him Mr. Komodo because he's crushing it with his speed here. Ran 1 mile in 4.695 minutes. Or maybe we could say, we really shouldn't, we should say Dennis's speed was 1 mile per four. Okay, let's try this again. What happens if I do Control Z? No, that's not helpful. So let's say this, maybe Dennis's speed was per 1 mile. Notice how this is subtly different. My first sentence suggests that he just ran for 1 mile. And he did not just run for 1 mile, he ran for 26.2 miles. So this is a little more accurate. Okay, and then finally we get a nice challenge question. What is his speed in meters per hour? So we need to convert, let's say, miles and minutes to hours if we run it from there. So let me jump to my pens again, and here we go. I'm gonna take the 0.213 miles per 1 minute, and I'm gonna do this conversion factor. So let's see, I know that there are 60 minutes in an hour. So if I multiply it by 60 minutes divided by 1 hour, these minutes cancel and we're left with miles per hour. And then I'm going to multiply by, let's see, 1 mile equals 1.61 kilometers. So I'll get my miles into kilometers. And I will get then my kilometers into meters. Notice in the end, I want meters on top and hours on bottom. So if I run through all the things that cancel out here, I already crossed out the minutes and we're left with hours in the denominator. Let's make sure Everything else goes away, miles and miles go away, kilometers and kilometers go away, and we're left with just meters here. So just a little multiplication. Remember, in the math world, we're multiplying fractions in the math world. It's just top times top and bottom times bottom. And turns out the denominator is, they're all ones, so there's nothing to multiply out there. And so Dennis was running 20,575.8 meters per 1 hour. Seems super fast. I mean, this is the number we're more, most of us, I think, makes more sense to us because we don't think in terms of miles and in meters. All right. Last two questions are modeling questions, so we definitely need Desmo. So I'm going to get a new graph. Come on now, I don't need that mess. So this is blood pressure. Or sorry, not blood pressure. This is the pressure exerted the deeper you dive in water. So we're just going to fill in the data here. It says find a model of best fit. Well, we don't know what that model is. So we're going to put in the data and look at the graph and see if it's linear or exponential. But actually, just like you did in 527, we're going to find both a linear and exponential model and determine which of the two models better by looking at the R values. That's our tried and true method. Although I suspect when you look at this graph, you'll be able to tell which model it looks most like. So I got my data in. Hopefully it's correct. Hit this. Wow, that looks really linear. Now this 1.6042.21 felt like it was wrong, but it looks okay because otherwise it looks almost perfect. So I think we're good. It looks very linear. Let's do y1 tilde mx1 plus b. Look at that R value. That's essentially 1. Let's just double check exponential just to confirm that we're good. And we're going to convert that to log mode. It's a good R value for exponential, but it's much better for linear. And if you look at how the line fits the graph, the line is much better. Honestly, I think, which one is it that's messed up? This one. I think this number is probably wrong. It's probably a typo because I do believe it's just straight up linear. But anyways, we'll be happy with what we got. So our model is y equals, does it say? Oh, it does, 2 decimals. So y equals 0.44x plus 14.64. And then our R value here, it's essentially 1. It's 0.9994. If we're rounding to 2 decimal places, that would be approximately 1. All right, what about our y-intercept? What is that? Well, the y-intercept is the pressure at a depth of 0 feet. So the pressure at 0 feet is about, we'll put in about since this is from the model, 14.64, and you can see that value really closely matches the value that's actually in your data set. And then since this is linear, we're going to interpret the slope. So our slope is 0.44, and we'd say for each 1 foot increase in depth, pressure, which is the y value, increases by 0.44. What are the units on these? Pounds per square inch. Pounds per inch squared if we use units. All right, now we're supposed to predict the pressure at 100 feet. Now be careful. You're going to be very tempted if you encounter this problem on an exam or another worksheet. If this data value is actually in, if our data set contains this value, you're going to want to use it. but it says use your model, not the data set. So don't copy the value you see in the data set. Plug this in. This represents an x value. So plug it in. You're going to have y equals 0.44 times 100 plus 14.64. Well, what is that? I'm just going to let Desmos do it for me. I should probably be able to do it in my head, but there's no sense in not letting the robots give us the answer. Look at that, 58.64. A little bit different than the data set. Pretty close, though. So then we're to find the relative error of this. Now, this is the estimate. This is the actual. So here's why we had you use the model, because we also want to see that you can calculate the relative error. Remember, relative error is estimate minus actual divided by actual. And if we stick with the two decimal places, let's see what this comes out to be. 58.64 minus 58 divided by 58. That's 0.01103. As a percentage, if we did a percent to two decimal places, it'd be 1.10%. Pretty close, not a bad model. All right, here's another one. This is the last question. Hooray, we made it. So notice when I add a second table, well, this claims I'm adding a third table. I don't know why it went to x3, y3. It doesn't matter. Notice the subscripts on the x and y are a different number than 1. So when I do my models, I'm going to have to do a different subscript. So what is this data? This is the time, and then it's the infestation of cane toads in Australia. I'm assuming this is real data. I don't know. It's probably taken from a textbook. And I would be curious how these numbers look after the devastating fires of a couple years ago. You'll remember that mess? Doesn't it seem like there's a ton of crazy disasters going on in the world these days on top of a pandemic? I'm thinking Texas and other places with all that mess. Anyways, so here goes this data set. Oh boy, doesn't that look very obviously exponential? Right, that's got that nice curve going on. So we'll start with that one. I'm doing y3 tilde ab raised to the x3. That looks almost perfect, and using log mode, boy, that's really close to perfect. And then let's just show what the linear one looks like. According to our regression model, it's still a pretty good regression, even though graphically it looks quite terrible. Okay, so what's the model best fit? It's exponential. And notice, hopefully you're catching, when I write down this model, I no longer write that subscript and the tilde. I'm writing the y and the equal sign. And again, I'm rounding to two decimals here. So 36,163.1. There isn't any more decimals to go on that. And 1.08. Now, when you round an exponential to two decimals, you're going to create quite a lot of error. But that's okay. And then our R value here is exactly 0.99999 forever, which is rounded to two decimal places, is approximately 1. So what's our y-intercept? Well, notice these are years since 1930. So year 0 represents 1930, and that is the y-intercept here. If I plug in 0 here, the A value of my model is that intercept. So we'd say in 1930, there were approximately 36,163.1 cane toads in Australia. No, that's not quite right. There's this many toads per square mile. Or sorry, square kilometer. Kilometer because Australia rightly uses the metric system, unlike us foolish Americans. Okay, since it's exponential, we're going to interpret the growth rate. So this is the growth factor. Since we're told to do the growth rate, the rate is that 8%. So it's 1.08 minus 1, which is 0.08 or 8%. So we could say the infestation per square kilometer is increasing by 8% per year. That's not how you write a year. After 1930. So then we're to calculate what's this value in 1960. Well, we got to figure out what that x value is. So we're going to do 1960 minus 1930. Oh, it's 30. Now be careful. We have a data value for 30, but that's not what we're interested in. We're interested in what the model gives us. So I got to type my model into Desmos. And since we're told to round, we're going to use the rounding to be the same way when you take your exam. Just like in ALEX, you have to follow the directions in terms of rounding, since the computer is grading it. So I'm putting in a 30 here, and our value is coming out as, oh no, there we go. Y equals approximately 363,895.86. So it's 363,895.96 toads per square kilometer. So another practice, the same problem as before. What's the relative error with the actual value from our data set? So these are recorded values. These are estimated by our model. So we're going to do estimate minus actual. That's 363, 895.86 minus 352,900. Pretty close. Although it got a little worse, our model approximation is a little bit worse because we rounded to 1.08. That increased that growth factor significantly. Okay, so what percent off are we? Notice we're above by 3%. So this value is 0.0312, or we're over 3.12%, overestimated. All right, the next question is a trick, right? So we're supposed to figure out when is y equal a million. Well, just like I noted in the 2.7 work, you need logarithms to be able to solve this analytically or by hand. So I'm going to go back to this equation. I'm going to turn that into I'm going to write that. So I just typed out an equation, and then I'm going to type in y equals 1 million. And I can find this pretty easily. I just got to scroll a little bit. Here's the 1 million mark. Here's where they intersect. It's an x value of 43.176. So we want to show our graph. Here's the graph showing how we got this. I do believe that this piece, give the max and min, is a typo. There are no maximums or minimums in exponential functions. They don't exist because they go on forever. Now, it said in what year, just like the other one. We found how many years after 1930, so we're predicting this to be 1973 that we'll hit the 1 million toads. If you look at the graph is just growing exponentially, and it will never stop, mathematically speaking. But there's obviously a finite amount of space in Australia, and eventually these toads are going to run out of food, and the population will not continue to grow exponentially. It'll grow like logistically. There's a logistic function that has a cap, an upper bound, so this thing grows up to that and then tapers off. That's really what would happen. All right, so this is the end of the Unit 2 Review A worksheet. Here's the B worksheet. Just like I said on the Unit 1, this was the exam I gave in class in previous semesters when we were in person. So you can figure out what it was like, see how it felt if you were sitting there taking this exam. And when I write the exam, the midterm, I'm going to take questions from these review sheets as well as questions from these worksheets, these practice worksheets up here. and type them into, well, not these, because these are 2. Chapter 4 stuff. But we'll put these in JetNet, and you'll give me a demonstration that you know some of this and that you can do it with just your own handwritten